Hello and welcome to my assignment 4 code, jumping right into it. This is for the racetrack. And define some key data structures, which I'll go through, which is our learner, our race, our track, our race car, and our value. Jumping right into it using the W track as an example. Our race is our key data structure here, which defines our actual race. And a race is consistent of a track and a race car, and I'll go into those. To define our track, we get it from our file path. Race car is something that we define independently. So jumping into our race, here's a constructor. It holds all of our functions relevant to running a race, and also one of our most important functions here is our start race, which is functions as our main method. From here, jumping into how the learner works, and before I do that, I have to explain one of the key things that the learner is actually updating. There's a metric, and there's an important note here. This is inside the track. Inside the track data structure, there's this value matrix map, which maps a vector to a value. And so our state, consists of a position and a velocity. So for our velocities, we have our -5 to +5 row and column. So that's actually 100 possible states per position. So this is the data structure that our learner is actually updating. So we go into our learner and here's our for loop, which iterates over every possible velocity. And then here's our while loop, which makes sure that we're calculating our utility correctly. So we jump in and calculate our utility. We have our original utility, and we iterate over every possible acceleration. I know it's a little messy. So we go into our Bellman update inside of here for every possible acceleration, and we define our state, our Q, based off of this right here, which is commented in. So have all this stuff that's optimizations for making sure we calculate our state correctly. And here's the meat and potatoes of it, calculating our Bellman value. So jumping back out to here, so we have our Bellman update for every possible acceleration. And so if our state is less than our minimum utility, then we make that our new policy. But we have multiple policies that can be minimizing policies. So if it's equal, then we also add that policy to the minimizing policy. And so when we get to it, as long as we are not a finishing state, then so we go to this right here, which selects randomly from our best policy list our policy for our value. So we jump back out, and that is how we're calculating our utility and our Bellman updates and our policy for this and our minimization. So we have our delta mean squared error here. So jumping back out, that's how the learner is working. Give me 1 second. So we jump in, we initialize our starting index of our race car starting point. We set the starting position of the race car. We initialize that there. We print the track, and then this is our while loop where our actual race is occurring. So this is our follow policy, which essentially follows that policy that we found through our value iteration and seeks to minimize that value to the finish line. So we update our race, we calculate our kinetics for our race car, and this is a good point to jog to our race car. Our race car has a position, velocity, and acceleration being the only thing we actually can control. So we have our kinetics here, which calculates our velocity, which is our acceleration plus our velocity, and then our position, which is the velocity plus our position. So we check if we finish the race, we make sure we're on the track, we update the track correctly, we make sure that we're not crashing in any way, and so we actually check our line collision right here. I know the line collision was fine, and just jumping into lines in general. So we have our line right here, we have our Breslin line code here. Coming out, so we calculate this and we print our kinetics, and so we go back to our race. So we're updating our race, we print the track, and so we check if we crashed. If we crashed, then we have to go ahead and adjust some policies with an optimization, which I talked about, and we reset the car based off of our Boolean right here, which is return to start on crash. And that's not true, then we reset to a normal value. But if it is true, we reset to the start. So we go here, we check if we finished, then we return. And we return our metrics. If we're spinning, then we have to shuffle some policies. If we crash too much, we shuffle some policies. And then when we crash way too many times, we cut because we're not doing anything. And if we spin too many times, we cut. We're not doing anything. So I'm sorry I missed this point right here, but just calculating our actual Bellman values right here. You can see we calculate over all of our possible accelerations. You can see our current point plus our next point, and then we have our actual Bellman update right here, which is 6.3996. That's our min utility. So we're adding all this stuff. Then all of a sudden we reach a 2.8, which is our new min utility. And so this becomes our best policy, which is 0 minus 1. Nothing else is that min utility. So our possible policies are 0 minus 1. Okay. So now actually running this to see if we can show you the functionality. So now we're iterating. We can see our little car going. He's going. And then we fall into here, which is great because then we get to see our car crash. We jump back and we go over here and then we try and make our way. We crash again and we come over here. Eventually he'll make his way. So we crash again. You can see that we're updating correctly. And while we're searching for that, I'll go ahead and talk about our kinetics. Here's our line drawing from 6.8 to 2.4, which is our pound sign, which is our wall. We can see our previous velocity plus our trajectory, projected trajectory, our current velocity, our acceleration, how many times we crashed and how many times we spun. Let's see how we're doing. Oh, we finished. Okay. So let's see if we can show a line clipping for you guys. I'm not sure if we will be able to because I think we finished correctly. But talking about line clipping really quickly, if this is a line clip, no, he slows down right there and he crashes and resets. This line between our position and our previous position, in here we check to make sure if there's a wall in here. If there's a wall, then we say our line collided. So even if we do jump over right here, we do successfully relay back that we collided. So coming down to here, we can see our metric. We finished in 51 steps. We crashed 4 times. We spun out 0 times. The total cost to finish is this. We return, and then our total learning iterations, min delta, this and that. And here's the actual value path that we took to get there. So we can see our policies that we took, as well as our positions, our velocities, and whether we crashed there. So that is everything that I have time for and everything that's important. Thank you.